find the shear stress at point B for the web plus flange. Okay. And this is also shear stress at point E for the web plus flange. Okay, so what we have found before, this is shear stress at point E of the web. Okay. So this will be equal to, so now we need to find the first moment of area for the web and flange. So this is straight, we just need to add up. So Q Z at point B or B, or first moment of area about the z-axis, point B for the web plus flange. So this will be equal to 3/2 plus 1 is equal to 5/2 inches cubed. Okay. So we are going to now find our stress at point B. Okay, so let me copy the image. Go next page. Right. So we're going to find the shear stress at point B, web plus flange. So this is equal to 2.75 times 10 to the power 3, 5/2. And I can't remember, I think it's 233/12. Multiplied by 1/8. Okay. So this is 2.75 power 3 times 5/2 divided by 233/12 divided by 1/8. So it's equal to 2.833 or 2833 psi. Okay. So this is also equal to the shear stress at point E, web plus flange. Okay, we were not asked to find this, but we are going to determine our tau max over here. Because the thickness are the same, the first moment of area is the biggest at tau max, or I'm going to call this at our point C, right? So we are going to determine the maximum shear stress at point C, which is our tau max. Okay. So we have to consider the first moment of area. Then let me draw the orange line first. Okay, orange line is where we take our dimension from. Okay. Right. So as the rules apply, we cannot, the first moment of area cannot cross the centroid. Right. So this is the centroid. So we want to find the tau max at point C over here. Okay. So Q at point C is equal to the Q of the web plus flange plus by the width. The depth is 6/2. The y bar is 6/4. Okay. Right. So this will be equal to 5/2 plus by half. Or I'll do this. Okay. So if you get confused. Okay. So that's our y bar. Okay. So 1/8 times 3 times 3 times 0.5 is equal to 9/16. So 5/2 plus 9/16 is equal to 49/16. So therefore, our shear stress at point C, which is equal to our tau max. So 2.75 times 10 to the power 3 multiplied by 49 over 16 divide by 233 over 12 and 1/8. Okay, so 2.75 power 3 times 49 over 16 divided by 233 over 12 divided by 1 over 8. So this is equal to 3.470 or 3470 psi. Okay. So it's not that difficult, right, to determine the shear stress point C. We don't need to calculate the width as 4 since it has the same using 4-inch, right? Tau tai, the dimension we take are all from the center line. Okay, so that's why I always draw the orange line. That's where all the dimension is acquired from. Okay, so that's why you don't need to minus 1 over the 16 like what you said. Okay. Okay, so you're good. Right. So this is all we are going to learn about shearing stress. And as I said, shearing stress is one of the most difficult topic. Okay, and you guys have survived. Okay, but you have to go through term test 2 for shearing stress. Okay, the next topic that I'm going to teach is not really difficult, but it's a combination of what we have learned and more. Okay, so I'm going to bring up an example for you. Okay, so the next topic that we are going to teach is going to be on combined loading. Combined loading analysis. Okay, so this is a big topic. Okay. Okay, so we're going to look at an example from here. Okay, so this is what we call the real world already. Okay, in the real world, the structure is loaded in 3D system, as you can see over here. So what we can see over here is we have forces acting in the x direction. Okay, we have forces acting in the x direction. We have forces acting in the z direction. Okay, and how does this affect the element H and the element K? So let me show you the what are the formulas that we have to apply and what are the analysis that we're going to use. Okay, so we are going to determine we're going to determine the stress state at elements H and K. Okay, H and K, where you see in this problem is the stress state that we want to see. But in real life, okay, where you position your elements is where you're going to guess where higher stress are going to be. So the position of the elements, note that position of elements in the real world is where maximum stress will occur. Okay, so when you go to industry, in the real world, you don't see element H and K at all. Okay, but you need to know where to position the element H or the region of analysis based on your best guess on where the highest stress will be. Okay, so you will not know at all. Okay, so before we can determine the stress state of element H and K, okay, so the first thing we're going to do is to determine the axial forces. Okay, you have to determine your bending moment. You have to determine your shear force. Okay, and before I write all this, I'm going to write down what I mean. So axial force, based on the transformation over here, we have to determine our px. We have to determine the bending moment. So for this case, based on this transformation over here, the bending moment will be in the y axis and z axis. Then we have to determine our torque, which is in the x axis, and we have to determine the shear force, which will be in the Vy and Vz direction, or Vy and Vz. So that's the first thing. Okay, we have to know what is our px. We have to know what is our bending moment by the y and z, the torque in the x-axis. Okay, later on I'll tell you how do we know the torque is not in the y-axis, why is it in the x-axis. Okay, and then we have to find our shearing force. Then the next stage, okay, you have to determine, okay, then we have to find normal stresses acting on the element. Right, acting on the element. And we are aware that the formula that we will use is normal stress in the x direction is equal to px over a plus by my over iyy multiplied by z minus by mz over izz multiplied by y. So this formula looks familiar. It's what we learned in the first 2 weeks. Yes or no? Okay. So for this case, we classified it as what? We classify it as eccentric, unsymmetrical, loading. Okay. So if we were to plot out the distribution now, okay, we're going to sketch out the distribution. So if we have normal stress or on our x-axis, right, then we have our y-axis. So this is our stress x. This can be our y or z. And we know that the distribution, this is just a sketch, okay? The distribution will look like this. know that the distribution will look like this, right? So we have compression,